Today, we are going to see some properties of eigenvalues and eigenvectors. Last class, we have seen how to calculate, given a matrix A, how to calculate the eigenvalues and eigenvectors. Now, let's see the properties of eigenvalues and eigenvectors. Given a matrix A, suppose it has n eigenvectors. Suppose A is a n square matrix. If there is a matrix of order n by n, then it will have n eigenvalues. Say lambda 1, lambda 2, and so on, lambda n are the eigenvalues of A. Then the first property is the sum of all those eigenvalues is equal to the trace of a matrix A. Trace, I mean sum of the principal diagonal elements. That is, trace of A equal to sigma lambda j. Right? You add all the eigenvalues, their sum is equal to the sum of the principal diagonal elements. Right? The product of the all eigenvalues, that is lambda 1 into lambda 2 into and so on, lambda n equal to the determinant of A. Right? If lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. So if lambda 1, lambda 2 and so on, lambda n are the eigenvalues of A, then 1 by lambda 1, 1 by lambda 2 and so on, 1 by lambda n are the eigenvalues of A inverse. Then if it's an orthogonal matrix, lambda is an eigenvalue of an orthogonal matrix, then 1 by lambda is also an eigenvalue, so that the product is equal to 1. We'll see that. We'll elaborate that in future. We're taking an example. Because orthogonal matrices, they play a very important role in future. Right? We'll see that in the coming slides. So, extending the topic. If lambda 1, lambda 2 and so on, lambda n are the eigenvalues of A, then you scale them like k lambda 1, k lambda 2, and k lambda n are the eigenvalues of the matrix Ka, where of course k should be a non-zero scalar. And what are the eigenvalues of powers of a matrix? Suppose lambda 1, lambda 2 and so on, lambda n are the eigenvalues of a matrix A. Then what are the eigenvalues of A square, A cube and so on? In general, A power p, where p of course should be a positive integer. Then its eigenvalues of A power p are lambda 1 power p, lambda 2 power p, lambda n power p and so on. Right? So these are the couple of properties. Right? As I said earlier, we are more interested in some symmetric matrix, or rather we'll see its general matrix, Hermitian matrix. Hermitian matrix has some specialities. Right? We'll see what are they. Right. Now, a couple of more properties. Eigenvalues of A and A transpose are same. Right? If a matrix is a singular matrix, right, then a singular matrix will have at least one non-zero eigenvalue. And the eigenvalue of a diagonal and triangular matrices are equal to diagonal elements. That is, the eigenvalues of an upper triangular matrix or a lower triangular matrix are nothing but the diagonal elements. And important property, the seventh one, distinct eigenvalues will always produce linearly independent eigenvectors. This is widely used property in future in our discussions. Right? The eigenvalues are distinct and the corresponding eigenvectors will be linearly independent. Right. Let's throw some light on orthogonal matrix. First of all, what is an orthogonal matrix? A square matrix A is said to be orthogonal if A transpose equal to I, or A transpose equal to A inverse. Right? As I said earlier, if lambda is an eigenvalue, then lambda 1 by lambda is also an eigenvalue. They come in pairs. Right? So that lambda square equal to 1 or lambda equal plus or minus 1. That is, determinant has the property plus 1 and minus 1. Right? Eigenvalues are real or complex conjugate pairs with absolute value of unity, right? Meaning norm of the eigenvector or modulus of that eigenvector, mod x will be equal to 1, right? When are two vectors said to be orthogonal? If x transpose x, xi transpose xj should be equal to 0, right? And of course, they are distinct, so j should be different from k. Right? This property we'll use in future, right? Here is a small proof. Eigenvalues and eigenvectors of an Hermitian matrix, they're always real. That is the basic reason we love Hermitian rather symmetric matrix, right? The same proof you can apply for a Hermitian. We are proving it for a general matrix. Automatically, it holds good for a symmetric matrix, right? Let A be a Hermitian matrix. Let X be an eigenvector. Then you know Ax equal to lambda x. And A is Hermitian, so A conjugate transpose equal to A. Right? Now take the equation 1. You take transpose conjugate on both sides. This is what we have. It happens. Right? Post multiply both sides by x. Right? Then x conjugate transpose, A conjugate transpose, whole conjugate transpose. You know it's A. This is what you get. Right? Then we know Ax equal to lambda x. Right? And finally, doing some algebra, you get lambda conjugate transpose minus lambda equal to this. Right? This is nothing but the inner product of x and x. That shouldn't be 0. 0. If it becomes 0, it implies that it's orthogonal to itself. That's wrong. That's an absurdity. So lambda star minus lambda should be 0. So lambda star minus lambda equal to 0 implies lambda star equal to lambda. That happens only if lambda is real. So the eigenvalues of a Hermitian matrix are always real. Right? And how about their corresponding eigenvectors? They'll always be orthogonal. So the eigenvectors corresponding to distinct eigenvalues are always orthogonal. Right? Proof is analogous. You can just go through. Right? Finally, you get this. And lambda I here, who is 0? Inner product of this, inner product I mean dot product, as we discussed earlier. Dot product of this should be 0, or lambda I minus lambda j should be 0. But lambda I minus lambda j cannot be 0 because lambda I and lambda j are distinct. So dot product of xi and xj should be 0. Dot product is 0, meaning they are orthogonal. Right? So xi and xj are orthogonal. So these two important properties we use in future. What is that? The eigenvalues of a Hermitian matrix or the eigenvalues of a symmetric matrix are always real, and the eigenvectors are always orthogonal, right? Of a symmetric matrix are always orthogonal, right? And we'll see what do you mean by geometric multiplicity and algebraic multiplicity. If lambda is an eigenvalue, suppose if it's repeated n times, suppose A is a 3 by 3 matrix, lambda equal to 2, 2, 3, meaning lambda is repeated twice. That number of times, how many times it is repeated, is called algebraic multiplicity of lambda. That is here in the case algebraic multiplicity of 2. The algebraic multiplicity of lambda equal to 2 is 2 because it is repeated twice. And how many linearly independent eigenvectors it has got is known as that is the difference between the number of unknowns and the rank of the corresponding matrix A minus lambda I is known as the geometric multiplicity of the eigenvalue lambda. Right? Let's elaborate. Let's do an example. Suppose A equal to a matrix 3 by 3 matrix 1, 2, 3, 4, 5, 6, 6, 7, 8. Meaning the diagonal elements are 1, 5, 9. Right? Then the sum of the eigenvalues is nothing but the trace of A. So it's nothing but the sum of the eigenvalues. What I mean is lambda 1 plus lambda 2 plus lambda 3 equal to a 1, a 5, 1 plus 5 plus 9. Similarly, the product of eigenvalues, lambda 1 into lambda 2 into lambda 3 is equal to determinant of A. That is, what is lambda? Lambda equal to 1, 2, 3. What is the product? 6. Okay, that should be equal to the determinant of that matrix A, right? If 2 is an eigenvalue of a matrix A, then the eigenvalue of A inverse will be 1 by 2. That is, lambda equal to 2, 4, 6 are the eigenvalues. Then the eigenvalues of A inverse are 1 by 2, 1 by 4, and 1 by 6. Right? If 2, 4, 6 are the eigenvalues of a matrix A, then the eigenvalues of A square are 2 square, 4 square, and 6 square. Then the eigenvalues of A cube are 2 cube, 4 cube, 6 cube. And in general, the eigenvalues of A power P are 2 power P, 4 power P, and 6 power P. Right? Okay. We'll stop here and we'll meet in the next topic.